our world and beyond, space, in partnership with the European Space Agency.
A dry, hostile environment, just sand and stones. It's like being on another planet. This Martian landscape belongs to Earth, however, at the foot of the Teide volcano in Tenerife on the Canary Islands.
We selected this environment because it's very close to Mars, to the Martian environment, in terms of what the cameras will see, in terms of what the landscape will look like, in terms of what the morphology, the structure of the surface will be, and also to some extent also the soil.
It's hoped the Proviscout project led by Gerhard Pau will answer questions of mobility in a hostile environment and data transmission, two of the major obstacles facing the European Space Agency's ExoMars mission.
One of the real challenges in future will be to bring down the optimum data with the limited data rate that you have. That means you cannot just capture images, thousands of them. You have to select tens of them within a day. And we are combining the challenge of autonomous moving on the surface, autonomous locomotion with automatic selection of interesting targets.
Back in August, NASA successfully landed its car-sized robotic rover Curiosity on Mars. Its goals include investigating the Martian climate and geology, preparing for human exploration, and especially the search for microbial life on the Red Planet. Rome is home to the world's oldest scientific institution, the Accademia dei Lincei. This is where experts from all over the world explore the solar system and, of course, Mars.
What is new with ExoMars, with the rover in particular, is what we call the mobility. Mobility not only horizontal, but also vertical.
Just like its American colleague Curiosity, the European ExoMars will roam the entire surface of the Red Planet and send back photos and sample analyses from its surface. But its main mission lies deeper.
We will be able to sample material from below the surface that is quite important to understand if there is any sign of past life activity on Mars.
ExoMars will dig up to 2 meters deep into the Martian soil. The rover will of course analyze the Red Planet's geological composition, but what it's really looking for is some kind of trace of past or even present life. The search for life on Mars starts here on Earth, in the aptly named Rio Tinto River in southern Spain. This red water filled with heavy metals may hold some of the answers scientists are looking for.
En Rio Tinto hay unas bacterias.
In Rio Tinto, you find bacteria which can live in extreme conditions. This is why they're called extremophiles. The extreme conditions faced by these bacteria are very acid waters. The main characteristic of these bacteria is not only that they can live in acid waters, but that they themselves create this acidity. They use the energy from the iron for their metabolism and convert the water into sulfuric acid. So the waters are acid and the bacteria can live there.
These are the bacteria man is looking for on Mars, for they are the source of life as we understand it. We know that under Mars's surface lies ice, which could mean life on the Red Planet, including extremophiles.
Mars can help us understand things about life, about our kind of life. The problem we face when searching for the origins of life is that we only have one example. In science, that's a problem, because we have nothing to compare with. We do not know whether life elsewhere, if it does exist, has the same patterns as life on Earth.
This futuristic building in the suburbs of Madrid is the Spanish Space Agency's Astrobiology Center, a world reference when it comes to the study of carbon-based life.
El Centro de Astrobiología nació desde el principio con esa visión.
The Astrobiology Centre was created with the wider goal of discovering the origins of life. There are many disciplines involved. What we want to do is dig deeper in the areas where the disciplines cross over and where there is a lot of research to do.
Porque en las fronteras, en las interfaces de las disciplinas hay mucho trabajo por desarrollar.
We have astrophysicists, planetarian geologists who study the bodies of our solar system. We have prebiotic chemists who try to understand the chemistry which preceded life itself.
Previa a la aparición de la vida.
This centre is unique because it brings together all the scientific disciplines involved in studying the origins of life and forms of extraterrestrial life. Around 100 scientists from all over the world work here, and all the major space agencies are involved in the research.
There's also another department which is very important for us, the engineering department. It may seem far removed from astrobiology, but it isn't. Astrobiology has a very strong experimental component. If we want to find out whether life exists elsewhere, we have to develop and build new instruments with new concepts.
That is indeed a crucial part of research in general and of space research in particular. Much of the technology based on tools developed for research becomes part of our everyday lives. But the search into the origins of life goes much further.
We should not forget that ESA was able to deliver on Titan a probe to sample the atmosphere and the surface of this moon. That is quite interesting because we know now that there is methane and ethane in the form of liquid. And this was part of the still ongoing Cassini mission together with NASA and the Italian Space Agency, and the Cassini orbiter is still delivering wonderful information and data on the Saturnian system.
1.5 billion kilometers away lies Titan. Since landing there in 2005, the Huygens probe has been sending valuable data back to Earth. Scientists are particularly interested in the composition of its atmosphere.
There are very strong similarities between primitive Earth and Titan. Its carbon chemistry is very evolved. The only difference is the absence of liquid water on a permanent basis. So, understanding this chemistry will help us better understand what happened on Earth some 4 billion years ago, as there is no longer any trace of that today.
With Cassini-Huygens, it's no longer bacteria scientists are looking for, but the signs of life that preceded the appearance of living matter.
This allows us to study the stages which led to the complexification of matter. We're still very far from a living system, but we're looking at the process of complexification of carbon matter, which will eventually be able to reproduce.
In their laboratories, researchers reproduce the chemical reactions that take place on Titan. These reactions led to the formation of complex carbon molecules and solid particles called tholins.
Tholins are complex organic materials that are produced when you try to simulate an extraterrestrial environment in a laboratory. These are very interesting materials because we know that when they are put into water, they evolve into complex material.
Research on tholins takes us back to the very beginnings of chemical evolution on Earth. Did life on our planet appear through pure chemistry, or was it brought to Earth by other celestial bodies?
There's another object we're very interested in, and that's the comet.
Comets hold many secrets, including what lies at their core, which could contain the early signs of life. There's only one way of finding out: by going there. That's what the Rosetta mission is all about. Launched by the European Space Agency in 2004, Rosetta is heading for 67P, a comet millions of kilometers away. If it reaches its destination in 2014 as planned, it will drop off a small lander whose mission will be to transmit data about the comet's composition. Other life-searching missions are planned, including to Saturn's moon Enceladus and to one of Jupiter's moons, Europa, both of which have shown signs of life in the form of water.
And essentially, at the end, we don't look for life, we look for habitable zones. That means to look for places where all these elements are together in an environment that is compatible with the capability to develop life. That's why nowadays the research of these worlds is not limited only to our solar system, but it goes beyond, and we have to look for external solar system, for other moons, other planets around stars.
The first time a planet was discovered outside our solar system was back in 1995. Since then, scientists have counted more than 700 exoplanets as they're known. What they're looking for, of course, is a planet that might resemble the Earth with some form of life. What the telescopes are looking for are stars whose luminosity varies, indicating the passage of a planet.
What we do is point our telescope towards a planet we believe might be an exoplanet. It can take a long time. If we think it's interesting, we study it for several days. And in the end we say, OK, this is a firm candidate, and we pass on the work to the big telescope.
It's a lengthy process which requires the use of telescopes all around the world, night after night. What forms of life are we looking for on faraway planets? And do we have the scientific tools to find them?
First of all, the large telescopes have to confirm the data given by the satellite and the small telescopes, that this is indeed a candidate. Then they try to go a little bit further and discover the so-called life markers.
Understanding where we come from has always been one of man's greatest quests. One that reminds us about our place on this planet.
Nowadays we are working hard to understand how this Earth, this body was built and how life originated. For me it's also important to preserve this world and this life. And so we should not work only for exploration, but also for avoiding that we destroy what nature has built so far.
Life in this Milky Way with its hundreds of billions of stars, each hiding its own secrets, is enough to make the tiny specks of stardust that we are feel dizzy.